So where we left off is we were saying that, acceleration can have multiple variables. And so when we're integrating with multiple unknowns. So we can't just like straight integrate. And we also talked about the constant, where every time you integrate, you have to add a constant. So just to clarify with these constant rules, if I'm integrating x dx, the reality is this is x squared over 2 plus the constant. So you have to add in a constant when you're integrating, almost all of the time. Okay, so if you're just doing straight single integrals, you have to add in the constant. Okay, and the reason why I didn't show that right away is because I wanted to show why we need the constant, because we know that velocity the velocity as a function of time is also based on the initial amount of velocity. So if you have the integral of acceleration as velocity, that's at, but we're not including the initial velocity. So what we did say is we add a constant, where initial velocity is a constant value. So the initial velocity doesn't change. The initial velocity is given. So you have to add a constant, and that's how you get the more complete formula. So when you're integrating, you add a constant, and that's c. So I'm not going to talk about a whole bunch of that because this isn't meant to be like super in depth. This is just like explaining everything as quickly, the basics as quickly as I possibly can. Okay. So if I'm integrating something, what we said is we were going with y and we were going with t. Whoops. And the formula was like just y dy dt. So what we have to do is we have to do these separately. So we have to treat them separately, and we have to integrate independent, where we're saying so this constant is based on the idea that we don't have limits of integration. Okay, so if I have a limit of integration where I'm saying t goes from 0 to 2, okay, so I'm saying t goes from 0 to 2. So what I'm going to do is I'm just going to integrate this the way that I was taught. And what that is it's just yt evaluated from 0 to 2. So the reason that we don't need to do this is because the constant is because, as you say, at from up here, evaluated from 0 to 2, well, when t equals 0 is when the velocity is at its initial position. So we already have, if we put in 0 for t, we have initial velocity kind of already built in, is the idea. Okay, so that's the way that I was taught it. So we go yt from 2 to 0. So what it is y times 2 minus y times 0. And what we get is just 2y. And then we also now have to integrate with y, which is 2 times y squared over 2. And we're evaluating from, let's say y goes from 4 to 6. Right, so you have 2 times 6 squared over 2 minus 2 times 4 squared over 2. So I don't want to get into proving beyond what I said here, where if t is 0, that is the initial velocity. Or where t is 1, that is the initial velocity. So we're saying the initial velocity occurs when t equals 1. So what I'm saying is at from 1 to 2, is a times 2 minus a times 1, where this is the constant, which is the initial velocity. The initial velocity occurs when t equals 1. So we don't need the constant if we know the values that we're integrating over. So if I'm saying with my graph, what this is if I know my graph goes from 0 to 4, then I'm integrating 0 to 4, and I don't need the constant because the constant is right here at 0. So when I'm integrating 0 to 4 y dy, again, this is y squared over 2, evaluated from 0 to 4. So if I know the limits of integration, I don't need a constant. If I don't know the limits of integration, then I need a constant. So what this is 4 squared over 2 minus 0 squared over 2. So the constant would turn out to be 0 if we solved it. but we have the constant, it's right here. So we don't need to just put in c as a constant. The v initial is the acceleration evaluated at 1 second. So you have the acceleration at 2 seconds minus the acceleration at 1 second, where so the initial is known, and it's the initial value that we're integrating over. Okay, so hopefully that explains the whole constant thing, and that explains the double integrals as well. So if we're doing a double integral, we have to know the limits. So if we're doing double or triple integrals, we have to know limits. Have to know limits. It gets really crazy if you try to do it differently. Okay, so I'm going to go farther into Calc 2, where we're in 2 dimensions. So the way that Calc 2 works is before we said we had an area under a curve. So in Calc 1, we have this triangle. So what this is y equals x. So I'm integrating integral of x dx, x squared over 2, which is the area under the curve. Okay, but in Calc 2 we have 3 dimensions, so what I'm saying is I'm rotating this around at an angle that is theta. So now I have a volume